this computer. Okay, so hello to everyone. We are Machine Learning Together Milan, and we are today with Andrea Megaro. Okay, yes. This guy, this other guy with me, and today we will talking. We're going to talk about unsupervised learning for time series. Okay, it's a quite interesting topic in my opinion. He's the second meetup about this topic because in the first one we have introduced the main idea about unsupervised learning or time series, something in general. But now we want to go deeper in this topic. So we will start with Andrea's presentation, and after that we will see what we have seen in the last meetup, okay, and we will introduce some more interesting ideas about this topic. So I think that now it's your turn, Andrea, to present yourself and to present your topic.
Thank you very much, Julien. Yes, this is the topic of this lecture, of this series of lectures, unsupervised learning, and we will focus on multivariate time series clustering. As Julien said, this is the second lesson, but I will recap briefly the topics introduced last time. I will not bore you about this recap, but it is only to align our knowledge about this about the first part. Before starting, I want to introduce myself to the people who didn't had the occasion to participate to the first meeting. So who I am Andrea Megaro. I have a bachelor in mathematics for finance and insurance and a master in mathematical engineering at Politecnico di Torino, and with a Erasmus at EPFL, so École Polytechnique de Lausanne. I developed this strange device that you can see on the right part of the screen, and this is also my startup, my full occupation now. The name of this startup is Gymnasio, and it aims to bring well-being to everyone's life. So in this first product, we will focus on the home fitness market, and in particular, this device is a portable device that is able to evaluate your exercise that you are doing in front of this object, and it is able also to correct you. It fits perfectly also in small places, and to develop it, I used artificial intelligence, machine learning, and other kind of algorithms that allow also a personalized workout. If you want to go deeper into this project that I'm developing, feel free to contact me, and we can also discuss about it. But let's focus about this presentation now. This is the table of contents of this series of meetings. I presented last time the first chapter, but I will briefly recap it, and we are going to present the second one, so time series clustering analysis. In the first one, I explained the different ways to analyze data into the unsupervised context. But in this second chapter, I will deep on the real topic of these conferences, and so the time series clustering analysis. What to say about the first part? There are briefly, there are two types of unsupervised learning. The one that aims to reduce dimensionality, so to represent data in a low-dimensional space in order to explain in a more easy way data and to analyze better data. And the second that aims to look want to find homogeneous subgroups among other observations. This is the one that we will deep on. But yes, this is clustering analysis. This is the division of clustering analysis, but we will focus on the second type, and so partitional clustering. This is the explanation of what is one of the most famous algorithms of partitional clustering algorithms, and so k-means. But after this, we entered to the second chapter, in which we started to analyze not points in a common space, in a Euclidean space, but these objects. So this second chapter focus on the time series clustering analysis. And last time I introduced the context by telling that we are not considering points that are described by items, and so different points described by features, and so columns of a specific table. But we are focusing on multivariate time series. And what is a multivariate time series, and what is one point of the space that we are considering, and what is the objective of this chapter? Well, let's consider this graphical representation of a multivariate time series. We can see that there are multiple sensors that are represented by sensor 1, 2, and generic n, and we have some windows. How can we create this separation in windows? There are two ways. We can consider fixed windows, or windows that vary, that change according to the shape of the multivariate time series that we are considering. For a data mining purpose, we have to it is suggested to use the first way, and so to fix a length of time series, and to consider one point as the window composed by all different signals contained into one single window. So to make an example, in this case, I don't know if you can see my pointer, but the
yes.
first the first window is in this example is between time 0 and the first dot line, and the point is the merge of these n sensor signals. So this is one point in my space, and so distances are distances to evaluate the distance between points have to be evaluated according to this definition of space, of point, and a new measuring system. So we have to create, or better, we have to consider a ad hoc system. What is this system? What is this space? Let's begin by an example. So what is a Cn space, where n is a natural number? For example, 10. In this case, we have a vector space of complex valued finite dimensional space. So what is the norm in this space? It is the one that we can read in the slide. And what is the inner product that can be defined? The one written also here. So the summation of x and the conjugate of y. In this way, it's also possible to describe the norm in with the square and the square root. But we want to use a similar structure, not the one described by n numbers, but n by the number of signals that we have. So this is only an example to introduce you to the context, but this space is formed by objects that are contained into a space that assume that have value in the complex space, but in a matrix that have shapes n equal to the number of signals, and L that is times L that is the length of the windows that we are considering. So this is the space that we are considering. This is the norm that we can define, the P norm that we can define into this space, and the inner product is the one reported there. So this is the context, but according to what I said before, we have also to define what is the type of clustering that we want to use to divide in a homogeneous way all these points. What is the distance or the similarity that we want to use to evaluate if one point is distance is far or near to one according to one or another point, and what is the representative of one cluster that we have identified. So this is the table of content of next steps. Okay, so we want to use a shape-based approach. What it means? What does it mean? It means that we want to focus not on the different features that we can evaluate by starting from the shapes, but we want to consider the shapes themselves. To make one example, we can do a simple example about this with this graph. Let's consider the first window, and in particular the first signal. One feature that we can evaluate can be the mean value that this particular sensor recorded into the first window, and then we can annotate this information in the first column of a certain table. Then we can record in the second line the minimum value of the second window of the first sensor, and go on. In this way, we can create a table that summarize all the shapes of these windows. This is not the objective of this series of meetings. We want to consider the whole shape that characterized one window, particular of different sensors. So this is the meaning of this slide. And now,
Andrea,
yes.
can I say only a thing? I think it's very interesting because in the feature-based approach, I think that you are summarizing the information of your time series, but in the other cases, on the contrary, you are using the whole time series.
Exactly.
So I think it's a very good starting point for this kind of grouping.
Okay. Yes, it's this is the focus of the of this meetup. Indeed, if we consider a feature-based approach, maybe we can also not consider the time series clustering approach in this kind of work. Indeed, if we transform all the windows of a certain time series, multivariate time series, into a table, we can also consider a classical approach to the clustering of different points into an Euclidean space. So this is the point. It wants to be not a generalistic approach, but one approach that consider the different behaviors of the different windows of a certain multivariate time series. Yes, this is exactly the point. Indeed, this consideration can be also found into this chapter, the one that focus on distance / dissimilarities. Yes, this is crucial because if we want to understand this approach, the main part consists of finding the most effective dissimilarity to understand if two windows of time series are different or similar to each other. And what are the two most important, the two dissimilarities that I used? Let's begin by the dynamic time warping, also called DTW. This is the most famous one, and I want to briefly say you what is how it works. We start with two time series. I considered the univariate case only to be clear, but you can also extend this reasoning into a multivariate approach. So in the same way, you can extend this to the case that we are considering now. So let's consider these two time series, in this case univariate, and we have to build a matrix n by m, where n is the number of points of the time series x, and m is the number of points of the time series y. And in this matrix, also called cost matrix, in each point we have to put the distance, and with distance we mean a specific distance, a specific cost that we can use, that we can fine tune according to the different situation. In the practical case, we will also see what I chose for the case I analyzed. But in general, we can associate to each point for each combination of point of time series x and point of time series y, a different cost that can create the warping path. What is the warping path? So let's begin from the three conditions to evaluate the ideal path to go from point 1,1 until point nm. These three conditions can be summarized also by this image. That can be also a clarification of what I will say, but maybe we will start from the three conditions here. Maybe there is a problem with the connection.
Oh.
With my.
Why do you think there is a problem?
Ok, no, me l'hanno detto adesso, non importa.
Okay.
Okay, so the boundary conditions, the boundary condition is the easiest one. We have to start this warping path from point 1,1 until the end of the two series, so point nm. The monotonicity condition, that is to build a path that starts from point n1 and hence to point nl, and the step size condition. So we can do only a step of size 1 that can be 0, 1, 1, 0, or 1, 1. So in order to define the optimal warping path, we have to evaluate the summation of all the cost in all the different warping path from point 1,1 until point nm. And by doing this summation, we have to take the minimum cost among all possible warping paths. So in order to be clear, I have also I reported also this image. Let's consider these two time series blue and pink, or violet. Let's consider the x-axis, the one of the blue line, and the y, the one of the purple. So we evaluate for each point, and so in each cell we have the distance or the cost between cell number x-axis and cell y-axis. We have to evaluate all the possible paths that satisfy these three conditions, all these paths, and we have to find the one with minimum cost. So this is the objective. Why this is the more effective than the Euclidean distance? Well, this is for two reasons. The first one is because DTW distance can also evaluate the distances between two time series that has different length. So in this first slide, we have the X series that has n elements and Y n m elements. So they are not the same. And another reason is because the shift of this the shift that one series can have with respect to the other time series. Indeed, we have to create, as I said in the first slide, we have to create different windows that can also take into consideration different phases of the same phenomenon. In this way, if they are in phase, we have to consider the fact by minimizing the distance of these two equal signals, but with different phases. So these are the main two reasons of this effective algorithm. This is only a series of counter examples in order to understand better what is DTW is. So the first representation is correct. We have two. Before to start, we have two time series. The first 9 length, the first 7 length, and the second 9 length. This is the optimal path that I chose. But why this path, these 3 paths have not to be considered? The first one doesn't satisfy the first condition. So the property in which point 1,1 and point nm must be chosen. The second error in this picture is the one that we can see in point 5,5 and 6,4, in which we have a shift of the path of a negative shift. So we have here we have a -1 +1 shift, and it is not to be considered, as you can see here. And the third error is the step size the step size condition. Now, yes, maybe I confused the second and the third. Yes, in this counter example, the second error is the monotonicity condition. So the fact that from 5 we passed to 4. Yes, this is the error. This the third condition is violated here in the D picture, where I passed from 3, 4 to 0.47. Yes, here I did a bigger step than than the one that I can do. Yes, but let's continue to the second distance. So this is clear. This is maybe the most famous distance that one can see in this context. If there are no questions, maybe I can go to the shape-based distance, that another very famous distance. Julian,
I make only a point, Andrea.
Yes,
I think, in my opinion,
yes,
the reason why you want to introduce this similarity function or distance, whatever you want to name it, is because maybe you have the same time series or shifted. Okay, so you want to capture this factor that you have maybe the same time series, and you want to say, okay, we have the same type, the same kind of time series, and you want to say, okay, it's the same. And the second reason for the different length, okay, it's that maybe you have a bigger time series, and maybe it is the first one, okay, and you have another time series restricted, derived from the previous one, and the fact is that the second one is generated from the previous one, and you want to capture this point. So you want to say, okay, it's not another time series, but it's the same as before. Yes. Do you agree with me?
Yes.
So these are the reason, because you want to also to you want this similarity that can capture this fact, in my point of view. Okay.
Let's consider also the first restriction, that is the boundary condition. So if you take only a little piece of the first bigger time series, you have, in any case, conclude with the last point of the bigger time series. So
Yes.
you have also to consider this fact in order to do the right considerations.
Yes. If you have other questions, it's the time.
Okay, maybe I continue. Okay, this is another distance. Let's say improperly distance. All these two are maybe to be these two are effectively dissimilarities, not distances. But the reason is the one that I explained the time before, and is this maybe there is a. Does the boundary condition not allow for shifts in series? This does the boundary condition. Okay, the boundary condition allow for shift, but it is not the you have to consider that a minimum error must occur. So if the phase is exactly at the let's consider a sine and a cosine, and let's consider a windows that consider only a little portion. In this case, the boundary condition surely make an error in the first phases, in the first part, but then align the series in a center part, and then in the last part have to consider another error. So the boundary condition allow for shifts, but consider also this the quantity of the shift. So if these two series are perfectly aligned, the error is 0. If they are a bit not aligned, so in phase, but we can consider them aligned in a center part, but not in the whole series. So a minimum error occurs. So this is maybe okay. So this second shape-based dissimilarity, consider not this approach, but the one based on the cross correlation. So this distance ranges from 0 to 2, and consider the max cross correlation between two time series divided from their norm. So this is a number that goes from 0, from -1 to +1. 1 minus a number from -1 to 1 goes exactly to from 0 to 2 in this formulation. So what is the cross correlation with this omega? Well, it is explained right here. This cross correlation is the shift cross correlation. In fact, this one is evaluated between all the possible shift of two time series, and the omega index is the exactly what the specific index that allow the maximum of the cross correlation. In this way, we can consider the fact that I said before of the alignment, and can consider the maximum distance or cross correlation between two not in phase sequences. So also in this case we are considering this fact, but we have not the how to say the advantage of the first dissimilarity to be invariant with respect, not invariant, but consistent with respect to the dimension of the two time series. So in this case, we have two time series with the same length. Instead, in the previous case, we can also have different lengths. So this is the main difference. But in this two situation, we are evaluating two different dissimilarities that can work very well in one case, or in another, maybe it is more appropriate to use one of the two. So
it's like you are taking a time series and you shift the other one, and each time you compute the correlation in the end.
Exactly.
So you want to see if shifting the different time series, you can obtain a good correlation between them.
Exactly. If two time series are very similar but are not in phase, as we discussed before, they are they are aligned in this way by maximizing the omega parameter, and so we can evaluate the right shift of these two time series, and we can evaluate the right distance between these two. So this is the process that we are doing. So now that we can consider 2 points in this space, near or far away, according to these two different dissimilarities, we have also to evaluate one representative of a different cluster of points. How can we create a representative? So one series that can summarize all the characteristics of one cluster bench of time series. Well, there are three methods. I reported 3 examples of different methods, so they are not the only 3 the only ways to represent a prototype, but I chose exactly this to represent the different categories. So let's start by maybe the classical one, and so the PMM and the partition around the medoid. Let's consider endpoints of length m, and they have to be divided into k clusters. So C1, Ck. We have also to find this representative centroid, and with the first method, we choose the representative element by comparing all the distances between a generic element inside the Cj cluster, and we want to evaluate the summation among all the others. So what I am doing, I'm evaluating, I'm choosing the point of cluster Cj that is the nearest, as near as possible to all the other points inside the Cj cluster. So this is basically the idea. It is chosen among the other elements inside the Cj cluster. Why I emphasize this point? Because the second approach is completely different. Maybe we can say that it is the opposite. Why it is the opposite? Because we are considering the element that maximize the distance, and so the dissimilarity that maximize the dissimilarity, and so it has to be the as similar as possible to all the other elements, but all the other elements are not the one contained into the Cj cluster, but inside all Rm. And so if we are considering the length m and the univariate case, we search among all possible series in this space. We evaluate the distance with all the points inside the Cj cluster, and we evaluate another point that does not exist inside the Cj cluster. So this is the main difference. One is inside the cluster. The first approach choose a point inside the cluster J. The other approach take a point that is not inside the cluster that we are not considering. Then there is the third approach, and it is called, in this case, the DTW barycenter averaging. This approach, this is, as I said, this is only an example of this kind of approach. In this approach, we are doing this process. Let's begin with clustered time series. So it is assumed that time series are grouped into clusters. In this example, in the figure 1, 2, 3. So they are already grouped. Then all the time series in one cluster are shifted and aligned through the method explained in the DTW approach. And after this alignment, all these time series are all the corresponding elements are grouped, and the mean is evaluated. And so the resulting time series is the pointwise mean of the corresponding points in different situations. So let's see the example. It is easier. Let's consider Euclidean mean. Cluster 1. In the cluster 1, if we evaluate the Euclidean mean, we completely delete the hype that we have in the after the first part, because we are doing the mean of all different points in this in the range between 10 and 20 in the time axis. Instead, in the DBA approach, let's see the cluster 3. we have that the red curve, the representative of cluster 3, takes into consideration the spike after the first part, because all the elements of cluster 3 have been aligned before the mean that is done. So this is the main difference between the simple Euclidean mean and this barycenter averaging. So these are the three approaches that to consider in order to evaluate a centroid, a representative. These are the two distances to evaluate these the cluster itself themselves, and this is the approach that we are using. So we can continue with chapter 3, that is how to evaluate the goodness of this cluster that I built with all these passages. So before to continue, maybe I will do a little break to listen to questions or considerations.
I think it's quite clear. The idea is very interesting.
Okay.
And I really want to see the results of in your next meetups. I don't know, but I want to see your the results of this kind of algorithms.
Perfetto. Perfect. So this chapter maybe is the one that represent in a more clear way the sentence that I presented in the first lecture, the one reported at the end of chapter 1 maybe, and this is the courage that the data analysts have to tackle this type of problem. This great courage is well represented by all these different techniques to evaluate the goodness of a clustering process without knowing the right. We have a question maybe. How do we choose the window win in general? By simple search with incremental enlargement. Okay, this is a really interesting topic. Ilia notin, but we have a proper section that will talk about this part, and it is chapter 4. So keep this question in your mind, and we will talk about it maybe in this meetup if I have time, or maybe in the next one. But this is a very crucial point to do all the analysis with time series clustering. Yes. But before to talk about this problem, we have to consider something more related to the clustering itself. And so if a clustering division is good or bad according to certain measurement. So as I said also in the first lecture, there is an internal approach or an external approach. In the external one, we are using unlabeled data, but knowing the truth, knowing the real label that characterized every single day. In the internal approach, in the internal validation approach, instead, we are using a unsupervised dataset, and we are evaluating all the clusterings with an unsupervised approach. So I used only the internal approach. Instead, in the practical case, I haven't the ground truth, and so I decided to use only this. But external ones are very, very similar to the ones used in the supervised approach. So you can also find them in one of the articles that I cite here. Yes, yes, I didn't say it before, but all arguments are taken from a certain paper or certain book that is cited here at the bottom of the slide. So yes, let's talk about internal cluster validity indices. So what are we considering in order to evaluate if a division is good or not? These two are the main actors: the cohesion and the separation. The cohesion is the intra-cluster distance. So let's do a simple example. It's not not only the intra-cluster distances are the summation among all the distances between all the points inside a cluster, but it is only to make the idea more clear. So in one word, intra-cluster can be associated in one particular case to the summation among the distances of all points inside one cluster. For example, cluster red, cluster green, cluster yellow, or the inter-cluster distance, so the separation between the clusters. We can choose a representative of these clusters and evaluate, for example, distance between these two clusters. So these are generic terms, but as I said, we can go deeper on the different intra-cluster and inter-cluster distances. But very often these two distances are merged. Why? Because in order to have a more clear idea about this complex situation, we have to merge the information between cohesion and separation into one single index. And so what are the three approaches to merge these two informations? The first is the ratio type indices. So for example, the DAN index consider these two factors. In the numerator estimates separation by the distance of the two closest points belonging to different clusters, while in the second case, to the denominator, there is the maximum distance between all the points among inside one single cluster, that is Cm among all the clusters C. So this is the ratio between the diameter, and so the intra-cluster, and the inter-cluster, that is the numerator. Let's shift to the summation type indices, and let's consider the most famous one, and so the silhouette word. In fact, at the numerator we have a difference, not a ratio, but a difference between the distance to the nearest point and the equation, so the second term, that is the averaged across the distance point within the cluster. So average point within the clusters, and first term, the distance to the nearest point in another cluster. So intercluster minus intercluster distance minus intra-cluster distance. So these are two ways to merge the effects of these two type of distances, so intra-cluster and interclusters. And there is another one that consider both the inter and intra-cluster distances, but also merges the stability property of one cluster. In particular, in this case, we can see how the index can vary according to the removal of observation y. So we can remove one single observation, and we can evaluate the different performance of the cluster goodness. After that, we can average all these different performances, and after that we have an index between 0 and 1 that gives you the impression about the stability of the cluster. So if one cluster is not one cluster, but if one division of clusters is more or less how to say specific for this situation, and the proof is by adding or removing the y observation every time. So these are the three different approaches. The stability, considering one observation each time. This is one example. There is also another example by deleting one column or one column of the data set every time. So the stability of the clustering, and these other two ways to synthesize the inter and intra-cluster distance. So these are different ways to evaluate if one cluster division is stable, is well done, but a lot of CVYs can be evaluated. Here there is only a synthetic view of the different indices that I can evaluate for this right for this reason. But if I have this enormous number of CVYs to make a comparison among all different variables in order to find the right division, the right the best performances. How can I merge all these informations? What if the first index is if the first index say this triplet of variable is the perfect one, and the second index say, no, this other triplet is the perfect one. What I can do? Maybe this could also be a question to you to raise the attention. What is the solution that we can that you can find?
Andrea, I didn't get the last point. Okay, you have the different, okay, the different CY, and so
Yes.
you have to select the one or a combination of them. But I didn't get the last point.
Yes. The last point is every clustering division is based on different parameters. I said the prototyping function, so we have to choose the right one for my specific case. I have to choose the right distance, so I have also to decide this parameter. I have to choose the right number of k, and so the right number of clustering that I have to evaluate. So I have different parameters, and I have one data set. So I have to test this data set with all these parameters. After that, I have for all different permutation of this series of parameters, I have one result of silhouette, then index, cop, etc. For the second combination of parameters, I have another silhouette, then index, cop, etc. And so on. My objective is to find the perfect combination of parameters in order to create the best division possible. So my question is, how can I make a comparison if not all the different indices understand that a specific combination of parameter is the right one, is the perfect one, the ideal situation? What I can do?
Maybe, I don't know, you can decide to use a combination of them and create an optimization function that you want to, I don't know, maximize or minimize according to the how do you construct this kind of function, something like that. Or maybe in such a way you can decide an autonomous way for the parameter decision. In another case, you can create a matrix and see what is the best set of parameters that can optimize all the different CYs. I don't know, something like that, I think.
Exactly. The first answer that you said is the one that I will propose here, but all the proposal that you did are correct. So
yes, in fact, it's the same as Enrico. Exactly. Simply take an average, weighted average, exactly.
I could select the clustering solution that optimize a summary, average, maximum, minimum of CVI. The simplest is to take the average. Probably weird. Okay.
Yes, I think we have also to renormalize the different CYs because
exactly.
maybe they are saying something different. So you need maybe you can do an average, okay, but the weight is according to normalize them to make sense. Okay, I think it's something like that.
This is the way the ranking algorithm that I will present you act. And so what we are doing a comparison of CY that produce different lists. And with list, I mean all the different. Before of all, this is a already existing algorithm that you can find also in where I cite it. I didn't cite it. Yes, I will report the paper in which it is explained. And yes, this is a already existing algorithm that compare every single list that can be created between all the different combinations and evaluate this distance weighted with some weight W. The objective function is the following. We have to try to find the resulting delta star list that minimize the total distance with all the other lists. So we have all the possible lists that we can create among all the possible combination of parameters, and we have to find the delta star that minimize the summation of this this series of distances. What is the distance that we use? The Spearman foot rule distance. In particular, the second case, the weighted Spearman foot rule distance. What is it? This distance consider all these possible lists, but every position of this list is evaluated into the absolute value, and it is weighted by the difference of the two indexes that we are considering. And so this difference of CVY is the weight to consider one distance more, how to say, more bigger or smaller in the difference of ranking that we are considering. So let's do an example. One combination minus one another combination. We are doing the difference among these two lists, and we are doing the multiplication by the weight that is the difference of the different CVY that are giving to this difference, the first difference, so the ranking difference, the right weight. So this is the distance that we are using to this objective function. So at the end of this process, this is the end. So at the end of this process, we have the list that is nearest, as near as possible to all the other possible lists, according to all the possible, all the chosen CVY that you are considering. So this is the process, and this is the way we will act in the practical approach. So also with this other approach to find a solution to this complexity, I finished this third chapter, and maybe I also finished the second meeting, and maybe we will spend these last 10 minutes to the questions, and maybe the next time I will present the other techniques in order to complete the practical case. Only to I don't remember the name. Only to answer to Ilya Notin. the third slide of next, not the third, but the second slide is about the how to say, the table of content of this chapter, and the third part is about length identification. So if you are interested in this topic, consider to participate also to this other meeting. So if you want to do some questions, feel free to do some.
I think it's very interesting, this meetup, in my opinion. And the part that I will remind is the difference of the difference in the difference, but of the last part. But in any case, the general idea is quite clear, in my opinion.
Okay.
So
yes, obviously, in a meetup, it is different to go deeper and deeper in the different evaluation. But yes, I wanted also to transmit the idea that is.
I think the general idea is very, very clear. So you have to create the different cluster to evaluate them. So this point really rise up from your explanation, and in particular, okay, I think the most deeper details are very difficult to explain in
yes
5 minutes, and I think you need to explain also the mathematical concept behind them. But I think it's not machine learning to Milan is not the place where we can introduce theorems and whatever
exactly.
you want. So
exactly.
I think, but only to give the idea of what you have to do, it's in my opinion, it's very important. So yes. Very, very good meetup from my point of view. So if you have some other questions, some observation, if you want, I don't know, maybe Enrico can have some interesting observation in general. I don't know, from your experience, it's something that you think that can be useful for some application, for example. What do you think?
Maybe while we are waiting this other question, maybe from Enrico or other participants, all these algorithms that I presented today are available on R. And the next time I will explain also what libraries contains this type of already implemented algorithm. In particular, rank alg is the name of the package on R that you can use. So
yes, this is an interesting question from Elisa. In fact, can you make some example of the application of your topic?
Okay, so maybe let's begin from the second one that is easier.
The answer is no.
The answer, yes, the answer is I started with Python, so R is the second that I learned in the data science context. So maybe the one thing that I noticed is that Python is developing in this field, in time series field, but R is more performing from the library point of view, from this specific field, and so multivariate time series clustering, because as I said before, there are already implemented libraries that summarize all the things that I'm saying this evening. But for the first question, maybe I can answer you with the specific case that we will meet in the next time. Yes. If we consider some vehicles and so we want to consider cars, off-road vehicles, high airplanes, or different structures that have different components that are working together. This is the perfect case to use multivariate time series. Indeed, if you want to consider some aspects of these vehicles that are not the easiest one, so the one that can be identified by the human eye, you have to consider different signals of this vehicle, and you have to learn by these different situations that are characterizing different situation of this vehicle. For example, you can understand if one vehicle is on, is off, is doing something because you can see this something, but you cannot understand different different shape of the same action that you are seeing only with the human eye. So in order to obtain one help from the machine learning algorithms in the unsupervised learning context, you have to analyze all the signals that are running in that specific moment, and you have to understand if this situation is a pattern, is something that occur in some conditions, and now you can put your not your but the label that the algorithm understand. So this is one of the most important field of application, but I think that the most important in absolute is the biomedical engineering field. Indeed, not all, but a good part of this concept have been developed for the biomedical engineering field. For example, the DTW has been built also and firstly for this topic, and the idea is very, very simple. The human behavior is not something that you can divide in an extremely precision way only by looking at it. So if someone look at some behavior of one person, cannot assess the same thing about some inner behaviors, not the one that you can observe, but the one that are related to the brain activity, to the heart activity, to the blood activity, etc. So all the signals that came from the different part of the body can be arranged and studied in a specific range of frequencies, and this is another important topic in biomedical engineering. But all these specific frequencies highlights different behaviors, and in this way you can also understand the hidden behavior of a human being, of an animal, or another being. Yes, so this is maybe the most important topic in which we can find these concepts. Yes.
Yes, in particular, I was thinking about the fact that maybe according to this biomedical application, you can also study an anomaly detection problem, maybe with your Earth. I don't know, you have your signal, okay? You have the cluster associated to the signal, and after that you try to, maybe you have a problem, okay? You have a problem, and with this problem, your signal can change the cluster, can I don't know, maybe go outside of all the normal cluster, and you can say, okay, I have a problem, or something else, or someone else has a problem. So this
Yes,
maybe I think an interesting kind of application.
this is another. This is maybe yes. If you have a normal subject and then you have a subject that has some problems, or maybe not problem is the correct word, but anomalous behavior of another subject, yes, you can analyze the different clusters of the normal subject, and then you can make a comparison with the other subject. So this can obviously be another case. But the important thing is that this field of research is the oldest one in this type of application. So very interesting topic.
So I think that we can conclude for this meetup. Okay, so thank you, Andrea. Okay, so we have to see the last part in the next meetup. Thank you for everyone that participate to this conference. Okay, so I hope to see you again. It's not the next Monday because you have some
Yes.
troubles. So I think we will organize the next meetup on the Thursday or Wednesday, according to you.
Yes, absolutely.
Okay, so bye bye guys. And I want to remind the last thing, if you want to present one topic that you love, that you want to explain to the other guys in the meetup, we are very open, because the idea behind this meetup is behind Machine Learning Together Milan is to organize, is to explain our passion for data science, for machine learning in particular, or for statistics, whatever you want, and to expose a project, I don't know, maybe your master thesis, or maybe another project that you love, whatever you want. So it's very open, it's very appreciated from all the people here. Okay, so bye bye to everyone, and have a nice evening.